All right, guys, the goal of this video is to go through a pretty thorough explanation of the physiology underpinning diabetes, both type 1 and type 2. If you didn't see the previous videos in this section of the playlist under the endocrine system, make sure you check out the introduction to endocrine and the pancreas physiology so that you have a little bit of background on what's going on with insulin and glucagon. So I'm going to do a quick review of some of those things, maybe not in quite as much detail as the previous video, but just to make sure everyone's up to speed. The general goal here is we're trying to keep glucose levels in the blood as stable as possible. All right, so in this graph, you're seeing blood glucose up here. This is data from actual experiments with humans that got a glucose tolerance test. So at time zero, we gave these people some glucose, and in a normal healthy person, which is what these people are, you expect to see a pretty significant spike in glucose levels, starting somewhere around 70, 80, 90 milligrams per deciliter to begin with, spiking up into the 120, 130, maybe 140 range. If this person was diabetic, we would expect that number to go much higher. The next thing that you expect to see happening in an otherwise healthy person is they're going to get a really large increase in insulin levels. Right? Before this time zero time point down here, which is when this person was fed that glucose solution. It's like a glucose Kool-Aid, effectively. We expect their insulin levels to be pretty close to zero. Maybe not perfect zero, but really close because they're fasting at that point. Right? So everything before time zero would be this person is in the fasted state, just meaning they haven't eaten anything. They're surviving by pulling nutrients out of storage, right? Glycogen from their liver, fat tissue from adipose cells, that kind of thing. We want insulin levels to be low, and we want glucagon levels to be high during that fasted state. Makes sense? Insulin is your storage hormone. You've got nothing to store when you're fasting. And so you need glucagon. That's your release the energy back out into the blood hormone. Okay, so we give them the glucose levels spike, makes sense. Insulin levels also spike because, again, we're using that insulin as a storage signal to say, take that extra glucose out of the blood, stash it away in the liver or muscles as glycogen or in adipose tissue as fat or triglycerides. We also need glucagon levels to go down because, remember, glucagon is the hormone that tells your body to break down the storage and release it back out into the blood. We don't want to be doing that right now, obviously, because we have more glucose than we know what to do with, right? This person is effectively hyperglycemic here, right? Hyperglycemic just meaning elevated blood glucose above what we would normally want to see. So remember, in all of this, the endocrine system is really just a problem-solving system. The problem is glucose is too high. The pancreas is saying, hey, we're sending this insulin signal, this hormone, out to other cells to tell them to fix the problem. How do you fix the problem? You take that glucose out of the blood and you store it. And remember, this is a review from last time. Your main two storage options are glycogen if it's available, right? Your body only has so much glycogen that it can possibly make. And remember, glycogen is just stored glucose. It's a polymer of glucose, like linking together those glucose molecules like beads on a string. And so if you have a lot to eat as much as you want. You expect to have lots of glycogen. That dark purple staining is showing you granules of glycogen in the liver. If the glycogen fills up, you'll start converting your glucose into triglycerides, which are just how the body stores fat. And if that's the case, you would increase the size of these adipose cells, right? Each of these circles is one adipocyte, which is just a cell that's mostly filled with fat in the form of triglycerides. Those cells don't divide, they just swell and expand like a balloon. And so that's why these are from mouse tissues. This is an obese, right, overweight mouse. You see that its adipose cells are dramatically larger than those of the lean mouse because we've just been swelling those adipocytes full of more and more and more fat because we let this mouse eat as much as they want. Glycogen filled up, glucose can get converted in fat tissue. All right. Remember, you can also store glycogen in muscle tissue. We talked about that in the previous video. These granules that you see, this is under an electron microscope. So same idea as the liver. Remember, the only difference is this muscle tissue won't share its glucose back out into the blood again if you go back into the fasted state. it's going to keep that glycogen for itself as a form of energy currency. So when the muscle contracts, especially really hard workouts, high intensity muscle contractions, that glycogen is in like an internal energy source for the muscle to use, especially like those anaerobic type 2 muscle fibers that you probably remember hearing about in AMP1. All right. So in the end, what we're dealing with is, in the case of diabetes, the thing that type 1 and type 2 diabetics have in common is that they can't effectively remove glucose from their blood. And so diabetes really is a disease of hyperglycemia, right? We're going to go through type 1 and type 2 diabetes separately in a minute. But the main principle is, if you have this same glucose tolerance test that we saw with healthy people, we expect much, much higher glucose values in a diabetic group of people. All right, so what this slide is showing you is we've got two major variables in here in addition to insulin. There's a question of what you ate and physical activity levels. All right, so in this graph, what they did is they took people that were type 2 diabetics, rather early stage, right, low severity type 2 diabetics. And we had two different variables, right? They were either resting when they ate and after they ate, or they were exercising. And in this case, exercise meant a brisk walk, so nothing too intense, not like they were throwing them into CrossFit workouts, just enough to get some movement in. And then what they ate. HGI and LGI stand for high and low glycemic index. So high glycemic index, think very simple starches and sugars, right? White bread, pasta, soda, anything that hits your bloodstream very quickly. Low glycemic index, think things with fiber, fruits, vegetables, sources that are a bit more difficult to digest. All right, so what this is showing you is, same as the previous graph, time zero is when you give these people their glucose tolerance test. And in all cases, we see an increase. But in the people that were resting and ate the high glycemic index food, the starchy, sugary stuff, their glucose went through the roof. Right, this is in millimoles per liter instead of milligrams per deciliter, but this value is well over 200 milligrams per deciliter. It's very, very high. On the flip side, if you have them resting but give them low glycemic index foods, we come down a little bit. If you give them high glycemic index foods but have them exercise right after they eat, come down a little bit more. And if you eat the healthier low glycemic index foods and also exercise, then you barely have much of an increase at all, right? Dramatically less than in the other groups. And so the first thing I want to point out is this is specific to type 2 diabetics. For type 2 diabetes, it can very, very strongly be regulated and controlled and prevented by both of these things, right? Being more physically active and choosing carefully what kind of carbohydrates the person eats. All right, for a type 1 diabetic, this wouldn't work nearly as effectively. And the reason for that is type 1 diabetes is an autoimmune disease. By that, we mean the immune system is mistakenly attacking beta cells in the pancreas. Remember from the previous video, those are the cells that are actually making insulin, right? So your immune system effectively makes a mistake and misidentifies those beta cells as being something dangerous. Like, typically we would go after bacteria or viruses, things that are foreign. In this case, the immune system isn't very bright. It doesn't know any better. The person mistakenly produces antibodies that stick to those beta cells, and white blood cells in the immune system don't know any better, and they kill them. So a type 1 diabetic simply cannot make insulin. And so the solution is we give them insulin therapy, which in a modern setting really just means an insulin pump. And that insulin pump acts sort of like a mechanical pancreas, right? Or a mechanical beta cell, even more specifically. So that when they eat carbohydrates and their insulin levels go up, their glucose levels go up, the pump secretes insulin just like the beta cell in a pancreas normally would, right? Now, type 1 diabetics can still reduce the amount of insulin they need by exercising and eating lower glycemic index foods, but they still will need the pump on some level. Okay, a type 2 diabetic is different. Initially anyway, they produce insulin just fine. What they are is insulin resistant. And the idea here is insulin resistance means that the person's pancreas is still secreting insulin, but their target cells are becoming less sensitive to that insulin. Remember, the target cell is the cell that has the receptor. And so it's almost like the pancreas is producing lots and lots of insulin, and it's sort of yelling at those target cells saying, hey, why don't you do something about it? The target cells are effectively, putting their fingers in their ears and ignoring the communication. They're saying, no, we've been overstimulated. This is too much. They're removing their receptors so that they're less responsive, right? It's very similar to a person that takes a medication, like a pain medication. If someone takes opioid drugs like OxyContin or fentanyl for too long of a time, they'll become resistant and they won't get the same amount of pain relief, and they'll need a higher dose and a higher dose. The exact same thing is happening here, right? This person's pancreas keeps sending more and more insulin to try to get the response that it wants, but it's being ignored, right? And so for this reason, it seems very odd, but you can see type 2 diabetics that actually have unusually high insulin levels, but their blood glucose is still elevated because, right, the signal's being ignored, okay? So we generally, at least early on, we don't want to give type 2 diabetic patients insulin therapy as a treatment because that's just going to amplify the problem even more, right? They already have resistance to insulin, and so if you overload their system with even more insulin, it'll just generate even more resistance. All right, now the caveat to that is, at some point, this person's pancreas may produce so much insulin that their beta cells get burnt out, probably some sort of oxidative damage from overproducing insulin. And at that point, a type 2 diabetic may need insulin therapy because they don't really have any choice. And at that point, they're effectively kind of behaving kind of like a mixture of type 2 and type 1 diabetes at the same time. All right, so to cap all this off, I have a quick research paper that I'm going to walk you through to show how this can happen in reality. What the researchers did in this clinical trial is they fed people two different sugars, either drinks sweetened with fructose or drinks sweetened with glucose. And these were otherwise healthy people. They weren't diabetic. And the goal was see if there's any difference in the way that these two types of sugar affect the body. And they did this for 10 weeks. Right, so a 10-week study of people basically replacing some of the food they eat day to day with extra sugar-sweetened beverages. And by the end of this, the differences were fairly significant in at least a few different ways. One of them was the percent changes in certain body fat areas. So there wasn't a massive change in total body weight, but intra-abdominal fat, right, the fat that builds up around organs like around the liver and the heart and the lungs, showed a relatively minor increase in the glucose group after 10 weeks and showed a pretty significant increase, 14% increase in the fructose group. And so it made it seem like these people were increasing the amount of fat that they had in their abdominal cavity. And that pairs with this second number down here, postprandial de novo lipogenesis, or DNL. That's a big word. Postprandial just means after a meal. DNL, de novo lipogenesis, means making new fats. And so the glucose group, 27% increase, definitely not trivial, but the fructose group, 75% increase. The conclusion with this seems to be that fructose, since it's only metabolized and broken down by the liver, is overwhelming the ability of the liver to use that fructose for an energy source, and it's being converted to fat instead. And so what it seems like is that they effectively gave these people low-grade fatty liver disease in a matter of 10 weeks. Right. The other thing that we saw is changes in the response to a glucose tolerance test. Okay, so everything that you see on the left side, this is the glucose group, the people that were given the glucose drink for 10 weeks. And this is the fructose group on the right. And they gave these people a glucose tolerance test at the beginning of the study and then 9 weeks later after having drank their sugar solution. And what you see is they measure glucose levels and they measure insulin levels for both groups. For the glucose group, they showed a minor increase from week 0 to 9, right? Solid line is week 0, dashed line is week 9. Minor increase, but it wasn't enough to be statistically significant, which is why we don't see those asterisks above the data points, is it just wasn't quite enough to be confident. And so if glucose had an effect on glucose and insulin tolerance, it wasn't really obvious. The fructose group, on the other hand, when they came back 9 weeks later, they saw very significant differences, right? Increases in the amount of glucose that they had in their blood after the glucose tolerance test, and increases in insulin, right? And so think back to the initial physiology of this. If you're showing an increased amount of glucose, that's this graph, and you're showing an increased amount of insulin, it just doesn't make sense. In a healthy person, if you gave them more insulin, you would expect their glucose levels to go down because that's what insulin does. And so this set of data is documenting insulin resistance. They made these people insulin resistant, right? Because now they're releasing even more insulin and it's not even working as well, right? Their glucose levels are higher than normal. And so effectively this like fructose heavy diet for 10 weeks or 9 weeks gave these people early stage type 2 diabetes. They're developing insulin resistance, right? Okay, so how can we screen for this? The last part of this, if we want to predict diabetes, there's a very interesting set of data here where they looked at fasting insulin levels and then a glucose tolerance test. And so they measured insulin and glucose in a bunch of different people, and they were trying to predict whether these people would get diabetes later on in life. For people with pattern 1, this is the normal pattern, right? If you give a glucose tolerance test, you expect insulin to go up, you expect glucose to go up, and then over the next couple hours, you expect them both to go down, right? These patterns 2, 3, 4, and 5 are increasingly more and more problematic. And so the percent chance of this person developing diabetes over the next 5 to 10 years goes up the stranger the results get, right? These people are fairly normal. They just don't recover as well as you would like. These people have a delayed response and it doesn't come down as much as you would hope for. Groups 4 and 5 have very odd patterns. Their glucose and insulin levels, insulin just keeps going up and up and up. Glucose levels stay fairly elevated and don't come back down. These people have, a 30 to 50% chance of developing diabetes at some point over the next decade, which is dramatic, right? And so these are people that were initially screened as being normal when they were fasting, but had very, very deranged insulin and blood sugar results after that. And that should be a red flag that they need to change something about their diet and exercise habits. All right. Okay, hope this was helpful. If you want to get all the videos, make sure you go to the full playlist so you can watch them in order. Subscribe to the channel so they all come through. And after this, we'll be moving on to other endocrine organs to continue moving through the system.